So this notebook will cover the basics of reinforcement learning. The objective of this demo is to touch upon 2 points. First, we will introduce the Openai Gym library, which is going to be super helpful if you want to do any kind of reinforcement learning, either do research or understand how it works, how different algorithms work. Once we do that, we'll also take an environment from the Openai Gym and train our first reinforcement learning model using policy gradients. So first, let's begin with the Openai Gym. So this is a Python library, which, as the name suggests, released by OpenAI. It's a bunch of different environments which you can play around with. There are simple environments such as these basic physics-based models, these pendulums or inverted pendulums, or cars driving up and down a mountain. There are also other more interesting environments such as these cartoon bipedal walkers or lunar landers or cars. And also other more complicated kind of environments such as Mojoko, where you have 3D models walking up and down with several degrees of freedom, and your goal is to try and control how they work. We're going to focus in the beginning on what's called the Carpool Environment. So this is a very simple system where you have a pole upright on a cart. The pole tends to fall down one way or the other. So as an agent, you can either push the cart right or left in order to make sure that the pole remains upright. So let's see how that environment would look like in OpenAI Gym. So we can make the Carpool environment, and let's maybe see what properties this environment has. So any such environment, the key things to keep in mind are the state space, the action space, and the rewards. So let's see what the state space looks like. So in this case, the system is a simple, it's an upright pole. So if you think about it, there are 4 degrees of freedom for the system, right? So there's basically the position of the cart, the velocity of the cart, the angle that the pole makes with the vertical, and the angular velocity of the pole. So there are 4 degrees of freedom, right? So in fact, for any environment, you can just probe the observation space. So the shape of the observation space will tell us how many degrees of freedom there are. And as you can see, there are 4 of them, right? So each of these 4 state variables are continuous variables. So they have both positive and negative values. So they're floating point numbers. Okay, so that's the state space of the system. You can also probe the action space, right? So the action space in this case is, there are allowed 2 types of actions: either push the cart to the right or to the left. And the only types of pushes available are unit forces in the left or right direction. So this is in fact a discrete action space, right? So there's a plus one in the +1 unit of force in the x-axis, or the -1 unit of force in the x-axis. Therefore, there's so it's you can think of it as like pulling arm 1 versus arm 2 of 2 levers. Okay, so this is the environment that we'll try to train a model over. But before actually doing that, let's also quickly see other types of environments that OpenAI supports. So one interesting family of environments is the it's called the Atari set of environments. So Atari, of course, was a bunch of classic video games from the 80s. You can see, if you remember, or if you've been exposed to these, you can see all kinds of interesting games. Some of them you may even recognize, Bank Heist and so on. This is Breakout or Arkanoid, right? Yeah. So what we will look at briefly is this game called Freeway. So Freeway, it's been reinvented recently in iOS, called Chicken Crossing. But so Freeway basically, you have a animal or a sprite trying to cross a freeway, and you can decide to either go up, down, or don't do anything. Just wait. So the three actions, right? And the goal is to go all the way, from one side of the road to the other, without, of course, crashing into a car. Right? So that's the freeway environment. So for that, let's have to import the ROMs, the Atari ROMs. Right? So let's do that. It's done. So once we make the environment, you can also probe it. Let's see what the environment says. So in this case, the state space or the observation space is probably to see what it tells us. So we examine variable. So here the state space is, in fact, the image itself, right? So instead of the degrees of freedom of the system, here the state space is a bit more complex. You can think of the image itself as a state, right? So each frame of this image is each frame of this this video is basically a color image, right? And that can be viewed as 3D a 3D tensor size 210 by 160, and that's the state space, right? And so these are standard RGB images, right? And what's the action space? Again, you can probe the action space. This would be just so as I said before, there are three options, right? So the three things that the agent can do, either go up, go down, or stay there. So let's actually see. We can even probe what the state spaces actually do look like visualize them. So if we, for example, just to state, just assign state variable, right? Let's see what this looks like. This should be an image. Okay, and this is an image, and you can actually maybe visualize it. So this is like this is like a starting point where all the cars are on the right edge, and the cars will go up and from right to left, and the avatar has to move from bottom to top. Yeah, we can also look at the action space and visualize how that looks like. So if that's also in the n variable. So if we look at the get actions meaning, if we call that method, then let's see. So this says no up, which means don't do anything, or go up or go down. So these are three types of actions in this case. Okay. Similarly, yeah. So if you query this this variable unwrapped get actions meaning, then you can actually also call specific actions here. So the up action, for example. So let's say you repeat the up action 10 times, right? What would that give us? Well, it would give us something like this, right? So here the avatar has moved up a little bit from bottom to top. Other things to note here. So there's something called the done variable. So OpenAI, the environment keeps track of whether the episode is finished or not. So for example, if you run into a car, or in the pole example, if the pole falls down, then the episode is done. So then the game comes to an end, and you have to restart. Right. So that's the done. But I don't know what really info does. State and reward. Yeah. So what state does is it produces the next state of system, right? And reward also, if there's any reward at that particular action, see what you get. Okay, so this is Openai Gym, and I'll encourage you to actually play around with several other environments and try and code up your own parallel agents if that's something you're interested in. But for now, let's just simply train a model for Carpool. Right? It's very simple. system. So let's see if we can do something with this. So let's make 2 environments. So the train environment and the test environment. You could just test on the train environment, but in order to make sure that your system is your RL agent is generalizable and actually just does not memorize a particular environment or sequence of actions for a particular environment. Because if you think about it, in games, it's possible, right? So there are many examples where people play games like Mario or freeway on video game consoles. But they're blindfolded, which means that they basically memorize the optimal set of actions. Right? So that's possible. In order to make sure that you're not memorizing, let's say that you have 2 separate environments. Okay. So set up the environments. So let's think about what we'll need to do in order to actually train an RL agent. So the core of the RL agent is the. So we'll train policy. We'll train the RL agent using policy gradients. So in this case, the core of the RL agent is the so-called policy network or policy net. For this very simple example, a shallow 2-layer network will suffice. So let's think about a simple 2-layer network, right? So two sets of say dense layers, okay, with the ReLU activation in the middle, and maybe we have some dropout just to make sure that training is fine. Okay, so let's so that's our network. It's as simple as that. How do we set up these the number of neurons in this network? So for that, let's that will depend on how many input variables there are and how many output variables there are. So we already know this, but if we, for example, probe the we have already done this before, but for the Carpool environment, there are 4 degrees of freedom, right? So the state space is defined via 4 variables. So the input dimension, the number of input neurons for this network, for the policy network, will be 4. Similarly, for the action space, right? So if I probe the action space variable of the training environment, as we discussed, to pull it out of shape. Let's start to do n is the number of actions, right? So in this case, the number of possible actions in this particular environment is 2. So either push the cart right or left, right? So therefore, the number of output neurons would be 2. Right? It's as simple as that. So we can set up a policy network with. Let's set up a policy network. So we'll instantiate this policy network class with the 4 input features or 4 input neurons, right? 2 output neurons, and let's say we have 128 hidden neurons. This is something you can choose. Oops. Oh, I didn't define this. Okay, so let's define this. Right? So yeah, so this is our network. Okay, let's see how our network looks like. So if I print the policy network, yeah, so we have now a shallow network, 2 layers, as we instantiated about this. Okay, so that's all. That is the core of the RL agent. That's all we need. And also set up an optimizer, which is you can pick your favorite optimizer. In this example, we will use Adam. Cool. So that's the first step in building an RL agent. The second step is now to compute gradients. So unlike regular feed-forward networks, convolutional networks, computing the gradient is a bit more involved than just say calling loss.backward and optimizer.step. The reason for that, as we discussed in class, is that gradients are not well defined for standard RL in the standard RL formulation. Instead, we have to approximate gradients using the log derivative trick. Right. So we'll have to, if you remember from class, we have to sample a bunch of trajectories or rollouts, right? Measure the rewards, the returns, right? And then once you measure the rewards, then you multiply that with another log of the policy, the output of the policy network. That's called a log derivative trick, and then you take an expectation over all the trajectories. Okay, so it's a bit more involved. So let's try to code that up. So here, I've written a function here which calculates the returns. So this is just as we discussed in class, it basically computes the for a sequence of rewards, computes the expected discounted return. So the discount factor is gamma, right? So it's some number which you set between 0 and 1. Right? Also, it's in practice common to normalize the return, so to make sure that the returns don't blow up too much. So we will also just scale it up and down, right? So that is just a return calculation. So so once you have the return, now you can create gradients. So if you recall from our notes, if you go back to our notes, this is in our notes, the derivative of the expected return is nothing but the expectation of the return times the derivative of the log of the policy, right? So this is the log derivative trick. Okay, so that we can actually code it up here. So the update to the policy, this is basically what we would call gradient in supervised learning, right? So the gradient is nothing but the return times the log of the policy, right? So that's the so therefore the derivative of the reward is basically negative of the loss. So loss is negative of the reward, derivative of the loss. So the loss dot backward will give me basically return times the derivative of the log of the probability, right? Because this is the parameters are sitting inside here. Right? So this is what the policy network actually computes. Okay, so let's do that. This is our gradient computation procedure. So now we're ready to train the network. Again, here this is a somewhat more involved, right? So at each stage we have a policy network, right? It will produce some actions. Now we don't know whether the actions are good or bad. So in order to improve our actions, what we need to do is to, for that given policy, sample a rollout or sample a trajectory, right? Compute the expected discounted reward. Okay, and then use the log derivative trick. Once you compute the reward, use the log derivative trick and use that to compute the update to our policy parameters. Right. So the rollout procedure will be computed using the environment. Right. So the environment will be used to simulate rollouts. Okay. Right. So that's done it's done by calling the environment, right? So we'll have an environment, right? And then we will start with some state, right? Produce an action, right? Using our current policy network, and now we'll sample. So we'll sample the from the distribution produced by our policy network. So keep in mind that the policy gradients, everything is probabilistic, right? So the policy is also probabilistic. The policy network will produce a distribution over actions. In this case, in our particular case, the action space is binary. So this will be a binary, this will be a distribution over two symbols. Right? So we will construct that distribution and then sample an action from it. Okay, that's important. So while training, we don't compute the best possible action. Instead, we sample from the distribution of actions. This also relates to what's called the exploration-exploitation problem in RL. So we don't necessarily always choose the best action while training. Right? We also explore other possible actions. But that is achieved by this sampling procedure. So figure out the action. Look at the log of the probability of that action. Right. That's and then apply that action to the environment. That will lead us to a new state and produce a reward. Right. And then keep track of the rewards as well as the actions and as well as the log probabilities. Right. So this procedure will simulate a trajectory until the episode is done. Right. So if it is comes to an end, then that's the end of the trajectory. Okay, so this is the sampling procedure. So we have a sequence of rewards and a sequence of log probabilities. We will call a function that we wrote above to compute the returns and then update our policy. So this is it. So this is the training procedure. Okay, so this is all we need really. On the side, we'll also write a testing procedure, okay, evaluation procedure. This is basically the same as what we did here, right? The only difference is that while testing, we don't sample from the distribution, but rather we pick the best distribution. We pick the best action, right? So we don't sample from the distribution of actions predicted by a policy network, but rather we pick our best action. Right? So that's a slight difference between training and testing. Yeah. So the action that we choose in testing is always the argmax, but everything else basically is the same. We keep track of the rewards. Our goal is to basically maximize rewards, or find policies which maximize rewards. So if our policies are getting better, then the episodic rewards in the testing phase should also get better. Okay, that's about it. So that's just basically how you set up an RL agent. The rest is basically boilerplate. So we've done this a few times. Pick a discount factor. Usually it's picked to be some number between 0 and 1, but close to 1. Right? So pick a discount factor, some number of episodes that you want to train over, and also some number of trials that you want to average over. In this particular case, we will set a reward threshold to be 475, right? So this is if the last 25 trials have reached an average reward of 475, then we claim that we have done well. Right? So that's basically a reward threshold, and the rest is basically calling the train and the evaluate functions that we wrote. Okay, that's about it. Let's see how we did. So as you can see, we start with kind of low rewards, right? Like mean test and mean train rewards are kind of low, but as you can see quite quickly, it starts increasing, right? So both train and test are increasing. In this case, it's a lucky day because it seems that test is generally higher than train, which is good. This is again a very shallow network, right? It's a 2-layer network. Training should be very, very quick in this case. Typically in RL, state spaces are large. For example, in the freeway game, state spaces are images, right? So you'll have to probably write a convolutional kind of policy gradient network, many more parameters. Even though the state space is small, the network itself will be quite large. So RL generally takes quite a long time to train. So keep that in mind. But in this case, super simple network, it took a few seconds. Reward threshold already reached. Right? So if you want to visualize how we did, here's a plot. So we wanted to reach this bar of 475, right, expected reward. So blue is test reward and orange is train reward. You can see that they kind of track each other more or less, right? But in the end, they all kind of go up and eventually stay up. You can see that there's a lot of noise, a ton of noise. It's really, really noisy, which is unlike, for example, supervised training, right? Like in previous notebooks, we have trained feed-forward, classifier type networks. There, I didn't really jump around as much, right? Like there was a bit of stochastic fluctuations, but overall, trends were quite clear here. In RL, on the other hand, this is to be expected. There's a ton of fluctuations, lots of local minima all over the place, and it's entirely possible for policy to change nature quite quickly. So keep that in mind, right? So if, for example, we stop training after 100 episodes, may not have been ideal, right? Even though we had kind of reached the reward. So it's always good to see if your test reward persists for a certain amount of time before stopping training. Okay. So this is a quick demo of reinforcement learning. You're being intrepid. Feel free to use something similar, exactly same algorithm to train an RL agent to solve the freeway environment.